In this video, I'd like to consider the behavior of a torsion bar that is built in at two ends and subjected to a point torque. So we'll put a point torque right in the middle, let's say T naught, acting in the center of the bar at L over 2, and we'll assume that the combination of G times J, the polar moment of inertia, is a constant. So we'd like to find the rotation field for this bar, so as a function of position. So we'll measure position Z from the left end. The governing equation, because Gj is a constant, will be Gj phi double prime plus the distributed torque is equal to 0. The distributed torque in this problem is a point torque, so that's represented by a delta function, T naught delta of Z minus L over 2, so we shift it to the center of the bar. And then we need two boundary conditions for our second order ODE, and that will be phi of 0 equals phi of L equals 0. So this is the problem that I need to solve. It's relatively straightforward. We have two boundary conditions, a second order ODE, so we'll integrate that twice, apply the boundary conditions to eliminate the constants of integration. So we'll start here. Gj phi double prime is equal to minus T0 delta Z minus L over 2. Integrate once, Gj phi prime equals minus T0 H of Z minus L over 2 plus a constant, so H being the step function, and then Gj phi is equal to minus T0 Macaulay bracket Z minus L over 2 plus C1Z plus C2. So C1 and C2 are my constants of integration, and I'm going to determine those from the boundary conditions. So phi of 0 equals 0 is going to tell me that minus T0, 0 minus L over 2 inside the Macaulay bracket, plus C1 times 0 plus C2 equals 0. And in the Macaulay bracket I have minus L over 2, so this is going to evaluate out to 0. And so we find out that C2 equals 0. So we've determined one of the constants of integration. And now we can use phi at L equals 0. That's going to tell me that minus T0 L minus L over 2 inside the Macaulay bracket plus C1L equals 0. So inside the Macaulay bracket here I have L over 2, which is positive, so that'll evaluate to L over 2. So when I solve for C1, I'm going to find T0 over 2. So that's my other constant of integration. So my final solution, phi of Z, is equal to 1 over Gj times minus T0 Macaulay bracket of Z minus L over 2 plus T0 over 2 times Z. So that gives me my final result. And we can make a plot of that. So put phi on the vertical axis, and let's mark off some points L over 2. For points Z less than L over 2, the Macaulay bracket here is going to be negative, so it'll play no role. And so we'll have T0 times Z over 2 Gj. So if I go ahead and plot that, that's a straight line all the way up to there. And then for values of Z greater than L over 2, the Macaulay bracket will kick in, and it'll give me a straight line too. So not quite symmetric as it should be in my drawing. So maybe we can improve the graph here just a little bit, just to make it a bit more realistic. Just a sketch anyways. Looks a little bit better. And the maximum value here is going to be T0L over 4 Gj. So it's 0 at the two boundaries, and increases linearly to the midspan, and then decreases linearly out to the end. So, and just as a reminder of what these functions look like, so if I want to plot h of z minus L over 2, that's a function that's 0 until I get to L over 2, and then it jumps up to a value of unity there. If I plot the Macaulay bracket, x minus L over 2, sorry, I guess we're using z here. So if I plot, in this case here, this is out to L over 2, it's 0, and then it takes on the value of the argument. So the slope here is 1. And what's also useful to know are the integration rules. So the integral of the delta function is the step function, obviously plus a constant. The integral of the step function, so let's put some arguments in here, is the Macaulay bracket plus the constant of integration. And then the integral of the Macaulay bracket to a power is equal to the Macaulay bracket to the next power. So it looks like the usual rule. You just have to keep the Macaulay brackets around, and the definition of the Macaulay bracket is that it's either 0 or the value of the argument, and it's 0 if the argument is negative, and otherwise it's just the argument. Okay, so that's just a quick review there.